Hello, everyone, and welcome back to our series on vibrational spectroscopy. So far, we have focused primarily on the theory behind infrared absorption. We discussed molecular vibrations, group frequencies, Frank Condon transitions, vibrational progressions, and the factors that shift vibrational frequencies. But now it is time to move from theory into instrumentation. Today we ask a very practical question. How do we actually measure infrared absorption experimentally? How does an IR spectrometer detect molecular vibrations and convert them into spectra we analyze in the laboratory? That is exactly what we explore today. Historically, infrared spectroscopy developed through several generations of instruments. Broadly speaking, there are three major types of IR instruments. Let us briefly examine each other. First is dispersive spectrometers. The earliest widely used instruments were called dispersive spectrophotometers. These instruments use a monochromator, usually containing a prism or diffraction grating. The purpose of the monochromator is to physically separate infrared radiation into individual wavelengths. The instrument scans through the spectrum one wavelength at a time. The second category is Fourier Transform spectrometers, commonly called FTIR spectrometers. These instruments operate on an entirely different principle. Instead of separating wavelengths mechanically using grating, FT instruments use a device called an interferometer. Rather than measuring one wavelength at a time, the instrument collects information from all wavelengths simultaneously. This dramatically improves speed and sensitivity. The third category includes non-dispersive infrared photometers. These instruments use specific filters or absorbing gases to detect selected wavelengths. They are commonly used in dedicated gas analysis systems. For example, carbon dioxide monitoring, carbon monoxide detectors, and atmospheric gas sensing systems. Today, our focus will be on the revolutionary shift from dispersive IR spectroscopy to Fourier Transform infrared spectroscopy. Let us understand why FTIR technology completely transformed into infrared spectroscopy. If you entered a chemistry laboratory during 1960s or 70s, you would almost certainly see a dispersive IR spectrophotometer. At that time, these instruments dominated analytical chemistry. But beginning in the late 1970s and especially throughout the 1980s, a dramatic technological shift occurred. FTIR spectrometers rapidly replaced dispersive instruments for most infrared applications. Today, FTIR systems are the global standard. The- why did FTIR replace dispersive instruments? The answer is simple. FT instruments are vastly superior in performance. Let us examine the advantages carefully. First advantage is speed. A dispersive spectrometer scans wavelengths one at a time. This process can be relatively slow. In contrast, an FTIR instrument measures all wavelengths simultaneously. As a result, a complete spectrum can often be recorded within a second, sometimes even fraction of a second. Second advantage is high signal to noise ratio. FTIR instruments also produce dramatically better signal to noise ratios because the instruments collects radiation from the entire spectrum at once. Much more source energy reaches the detector. This improves sensitivity and spectral quality. Third advantage is reliability. Dispersive instruments contain many moving optical components, whereas FT instruments by comparison contain fewer mechanical scanning elements. This improves stability, alignment, and long-term reliability. The fourth advantage is better energy throughput. Now, this point is extremely important. In a dispersive spectrometer, the monochromator selects only a tiny fraction of the available radiation at any moment. Most of the source energy is effectively discarded, but an FT instrument uses nearly the entire radiation beam simultaneously. This dramatically increases optical throughput and sensitivity. So, how does an FT spectrometer achieve all this? Instead of separating wavelengths using a grating, the instrument creates an interference pattern using an interferometer. The interferometer splits light into two beams, changes their path lengths, and then recombines them. The resulting interference pattern contains information from every wavelength simultaneously. To understand this properly, we first need to review the concept of interference. When two light waves meet, they combine according to the principle of superposition. Depending on their relative phases, two things can happen. Constructive interference is if the peaks of both waves align perfectly, the wave reinforce one another, the resulting wave becomes larger in amplitude. This is called constructive interference. Now suppose the peak of one wave aligns with the trough of another. In this case, the waves cancel each other, the amplitude decreases or may even become zero. This is called destructive interference. Now imagine continuously changing the distance traveled by one of the waves. As the path length changes, the phase relationship changes continuously. This produces an constantly varying pattern of constructive and destructive interference. And this changing interference pattern is the foundation of FTIR spectroscopy. Like this, as shown in the figure. Now we arrive at the heart of the FTIR instrument, that is the Michelson Interferometer. The Michelson Interferometer was originally developed in the late 19th century by Albert A. Michelson. It became one of the most important optical devices in physics, and today it remains the core component of every FTIR spectrometer. The purpose of the interferometer is to create complex interference pattern needed for Fourier analysis. This combined interference signal is called an interferogram. Unlike traditional IR spectrum, which plots absorbance versus wave number, an interferogram plots signal intensity versus mirror distance. Initially, the interferogram may appear confusing or noisy, but hidden inside it is the complete spectral information of the sample. Now let us carefully trace the path of light through Michelson interferometer. We begin with the broadband infrared light source. The beam travels forward and reaches the beam splitter. The beam splitter is a partially reflective mirror. It divides the incoming radiation into two separate beams. Approximately half the light is transmitted and the other half is reflected. The first beam travels upward toward a stationary mirror. The beam reflects off this mirror and returns to the beam splitter. The second beam travels toward a moving mirror. This mirror continuously moves back and forth, and this movement is the key to the entire instrument. Because the mirror position changes continuously, the distance traveled by this beam changes continuously. This creates a constantly changing phase difference between the two beams. The two beams return to the beam splitter and recombine. Because their path lengths differ, the waves interfere constructively or destructively depending on the mirror position. The result is a continuously varying interference signal that is the interferogram. Pass passes through the sample. This recombined modulated beam now passes through the sample. Certain infrared frequencies are absorbed by the vibrating molecules in the sample. Other frequencies pass through the sample. The resulting beam reaches the detector. The detector does not directly receive a normal spectrum. Instead, it records interferogram. This interferogram contains all spectrum information encoded mathematically. Now comes to the role of the computer. The instrument applies a powerful mathematical operation called as a Fourier Transform. This algorithm converts the interferogram into familiar IR spectrum. Absorbance versus wave number. Why this is powerful? Because this mathematical approach allows FTIR instrument to collect enormous amount of spectral information extremely rapidly and efficiently. It is one of the greatest examples of mathematics transforming experimental science. Let us summarize today's lecture. There are three major categories of IR instrument: dispersive spectrophotometers, Fourier transform spectrometers, and non-dispersive IR photometers. Modern spectroscopy is dominated by FTIR instruments because they provide higher speed, greater sensitivity, greater reliability, and improved optical throughput. At the heart of FTIR spectroscopy lies the Michelson Interferometer. This device splits infrared radiation into two beams, changes their relative path lengths, and recombines them to generate an interferogram. Finally, a Fourier transform converts interferogram into a readable spectrum we analyze in the laboratory. In our next lecture, we will continue exploring FTIR instrumentation and examine how modern single beam and double beam FTIR spectrometers are constructed and operated in a real analytical laboratories. Thank you for watching. I will see you in the next lecture.